Hello, chemistry and physics students. I say both those because we are going to have this posted under both because it will be a review for physics students talking about unit conversions and SI units, scientific notation, and significant figures. Everyone's favorite significant figures. So we're going to talk about those in this video. But I also am posting, I'm going to be posting my buddy Dr. Lucas, who works at OU, and he has a video I'm going to post in there. So I think he does a fantastic job. There was a few things with like the calculator. I use a different calculator, so there's a few things like that would be slightly different. But you take the good parts out of it. Take the parts that apply to us out of it. So, anyways, we're going to talk about these things, and we're going to get started. So this is PowerPoints from the chemistry thing. So I can post this into the physics folder as well. We don't need my face in here. We'll pull this out there. All right. Feel free to pause the video whenever you need to. Okay, so base units versus derived units. A base unit is what is based on a certain phenomena or a certain exact amount or something that can be measured in a standard of measurement that we can use to base the other units off of. I didn't really do a good job of explaining that, but maybe an example will be able to be used. So the base units are used to make all the other units in it, and they have to be something that is unchanging. Because if you're a scientist in one time period, or even the same time period, and you do some calculations and some measurements, and then another scientist does some calculation and measurements, you want to be able to compare the results. You need to have some standard of measurement that is unchanging, so that when they do these calculations, that it is the same length or size no matter when you do it, across time, across continents. You need to have an unchanging unit. And the scientific community has continued to try to make units, base units, that do not change. And most recently, the kilogram was redefined. So if you're interested in a little light reading, look up Redefining the Kilogram. Fantastic. And their journey to make a unit of mass that is not changing ever. And some weird things happen that used to be just up until recently. These platinum iridium alloys, these very unreactive, very stable alloys that they made a certain amount of, they made it a certain amount, then they put it under triple vacuum and sealed them in vaults in Paris underneath the ground in vaults. And I think I'm just going from memory, but they did this, and but then they found that even those measurements were changing because we could measure it to such a high degree of precision and accuracy that they were able to find that these measurements were actually changing, so they needed to redefine it. So an easier one is the meter. Okay, the meter, they used to have a standard kind of stick that they used to made of that same type of alloy that was unchanging. But it still changes, so they needed a better thing. So eventually they came up with the distance that light will travel in one small tiny fraction of a second. And so that can always be found out. So that's kind of a standard that will never change. And time, I like the time. Time is based on the radiation from these vibrating cesium atoms. So atomic clocks are based off this, that they're measuring the vibrations of the radiation given off by the vibrations of these cesium atoms, and it's so regular that they can use it as a clock, an atomic clock. They're using atoms to base these time measurements off of. So when you have your phone or whatever gets a signal from an atomic clock, it readjusts it, because clocks will go off. They'll slowly drift off. So what will happen? So what it does is, when your phone goes out, gets a signal every day or 2 times a day, I don't know what it is, or maybe continuously, and gets the time from the atomic clock and readjusts its time to make sure it's accurate. There's one out in Colorado, if I'm not mistaken. And so they measure these things, and it's very, very accurate. I think if you had started an atomic clock at the beginning of our universe, then I think it would have only lost a few seconds at most, and that's over 14 billion years of keeping time, and it would only drift off perhaps a few seconds. But you'd have to look that up too. So a lot of this I'm pulling from memory. So a base unit, we have a set of base units in science, and this is the System International. We use the English system here a lot in the United States, and we'll need to be able to convert between them. But most of the scientific community uses these SI units, System International. So the time base unit is seconds, length is a meter, mass, kilogram, and so on and so forth. And you can read these. Copy those into your notes if you want to pause and take it, or just make sure you remember these. So what's the difference between a base and a derived? We'll just look at this quickly. Base, these are the base units. Derived use these to come up with other units. For instance, how fast something is going, whether it's a baseball pitch or driving in your car. We use miles per hour, but in these units it would be meters per second. Okay, so that is a derived unit because it uses more than one of these base units as its units. Acceleration we can measure in, say, meters per second squared, and force, which is we define as we'll use a Newton, but a Newton is actually a kilogram times a meter over second squared. So these are derived units. Are we recording now? Am I back here? There we are. Sorry. I was confused there for a moment. All right, moving on. We just talked about this. Second is based on the frequency of radiation given off by cesium atoms, and the meter is this fraction of a second, how fast light will travel in a vacuum. That fraction of a second. Kelvin is temperature. We need to be able to convert between Fahrenheit, Kelvin, and Celsius. So the Celsius scale, the Kelvin scale is the Celsius scale just shifted down so that absolute zero is the lowest temperature. So if we let temperature be the average kinetic energy of these substances, it only makes sense that if you have the lowest kinetic energy would be zero. So why don't we call it temperature zero? So they took the Celsius scale, the centigrade scale, and they liked that. They basically said we want 100 even increments between boiling of water and freezing of water. And that's how they said. So 0 Celsius is freezing, 100 Celsius is boiling, and then so that's they divided into that 100 even increments to know how big 1 degree, so 1 centigrade is. So Kelvin, though, they shifted that entire scale down so that basically 1 degree C is 1 Kelvin, the size of it anyways. But the scale starts at 0 for Kelvin, Celsius, and never goes into negatives. Centigrades or Celsius scales can go into negatives. So when you're converting between temperature units, you got to use the formulas for temperature conversions. We talked about derived units here. They use an example of cubic meters. Cubic meters is a derived unit because it uses meters times meters times meters. Or cubic centimeters is a derived unit as well. Density has a derived unit on it. It's a mass divided by volume. This is an important equation for you, so we're going to do several density problems. Density is mass over volume. D equals M over V. All right. One thing you need to be careful of, if you can fill in an equation, you can fill into any of these 3 spots, and you can solve for the other. Just make sure you're doing your algebra right, and make sure your units are consistent, meaning if you have density in grams per cubic centimeter, your mass better be in grams or your volume better be in cubic centimeters if you're solving for one of the other two. So that's an example. You must have dimensionally consistent units when you plug in. Scientific notation. We'll give a quick thing on scientific notation. So if you want to represent 800, you represent it in scientific notation has one number, 1 through 9, then a decimal point with the rest there, times 10 to some power. So 800 would be 8.0 times 10 to the second. And when you put it into your calculator, it spits out this, right? Well, it's the same number. It's just another way to represent it. Same here. 1, 2, 3, 4, 5 places to the right. And you made this number, if you move this to 3.43, you made this number a lot larger. You're going to have to multiply by 10 to a negative power to move it back to represent the same number. Remember, scientific notation is representing the same number just in a different format. So this is scientific notation. If you multiply it on your calculator, you will get this same number. Okay, here you move it over 1, 2. That's why it's times 10 to the second. Positive power, because you made this smaller and you need to represent the same number, so it better be multiplying by 10 to a positive power. Okay, so we can try one more. How about 5,320, sorry. How many do we move it? 1, 2, 3. 5.320 times 10 to the third power. Let's do one more. How about 0.024? And we would do 1, 2. So 2.4 times 10 to the negative second, because you moved it that way to the right to make it a larger number. So you better make this a smaller, a negative exponent. All right. All right. There's some rules for adding, subtracting, multiplying, dividing. If we need those addressed, we can do that. But if you want to think of I will address this, I guess, real quickly. If you want to divide or multiply the things that have the same base, so you have 10 to the third times 10 to the negative second. Well, let's make it negative. Oops. Let's just erase that. All right, forget this one. 10 to the third, say, times 10 to the fifth. You add, so this would be 10 to the third plus 5, which equals 10 to the eighth. Why? Because that's 3 tens multiplied out, that's 5 tens multiplied out, that's 8 tens multiplied in a row. That's why it's 10 to the 8th. You add it. It's weird, but it makes sense if you think about it that way. But what if it was 10 to the 3rd times 10 to the negative 5th? Well, you'd still add them. So it's 10 to the 3 plus a negative 5, which is equal to 10 to the negative 2nd. Okay, which is 1 over 100, because you'd move this down. That's actually 1 over 100. Or 1 over 10 to the 2nd. If you divide, you subtract. So 10 to the 5th divided by 10 to the 3rd is equal to 10 to the 5 minus 3, or 10 to the 2nd, or 100. Okay? So what if we have 10 to the 5th divided by 10 to the negative 3rd? That'd be 10 to the 5th minus a negative 3, which is 10 to the 8th. Okay? Okay, we're going to pause this, so we're going to stop this video, and I'll split it into another one. So we'll call this part A, and there'll be a part B.